In Lecture 2, we're going to look at integrated rate laws, basically a better way of analyzing rate data so that we can get a better, more accurate assessment of what is the concentration at a specific time, even into the future of the reaction beyond where we've recorded the concentration and time data for that reaction. The only real assignment that we have due is Chapter 13. That's going to be due Sunday, July 5th at midnight, 11:59 p.m. Eastern Time. I will hold that review session Sunday night, 8 to 9 p.m. on Blackboard Collaborate. And please start using the discussion board, really like an FAQ board. So any question that you have from lecture material or from homework or from any of the question, really, just post to that board. I'll take a look and answer as best I can or make a short video to help with that content. But I want it to be a resource for everyone in class, so someone else in class could look to that board and see that, oh, here's a similar question to what I had and here's the answer to that. Or to see, oh, okay, someone else had the same question. I'll just comment that, yeah, I had the same question as well, to give me a little extra kick to say, okay, now a couple people have this question. I need to sit down and put together a solution for that. But first, a little review from our last class. Our last class, we looked at rate laws and we looked at the rate law and reaction order with respect to individual reagents in the reaction. So for this hypothetical reaction, A plus B goes to C and D. If I were to tell you the rate law for that reaction is rate equals the rate constant times the concentration of A squared times the concentration of B, what is the overall order of this reaction? The overall reaction order is the sum from each individual component in the reaction. So this reaction is second order with respect to A, and it's first order with respect to B. Overall, we add those together, right? The sum, so overall, the reaction is 2 plus 1. The overall reaction is third order overall. The sum from A and B. The last thing we didn't get to from our first lecture is really what is this rate constant, right? So rate constant comes from the fact that rate always needs to be in molarity per second. The units of rate always needs to be molarity per second. Now let's take a look at a few of the rate laws to get an idea of where this rate constant comes from and what this rate constant is exactly used for, right? I told you it's used to help clean up the units from these calculations. So let's take a look. So for a generic first order reaction where the rate law is rate equals the rate constant times the concentration of A, right? We'll just say for a generic reaction of A going to B, and the rate law is rate equals rate constant times the concentration of A. What does that mathematically look like? Well, rate always needs to be in molarity per second. My concentration is molarity. So if I'm multiplying concentration and molarity by something and I need to have units in molarity per second, right, I need to introduce units of time from my rate constant. So to solve for my rate constant, I'm going to just divide both sides by A. So I have rate of the reaction equals rate constant times concentration. So I'm going to divide both sides by A. So if I take a look at the units, right, concentration cancels out and I'm left with my rate constant equals my rate divided by the concentration of A. So all I'm going to do now is plug in the units. So I know K equals the rate, which is molarity per second, divided by concentration of A, which is molarity. Molarity cancels out. The units of rate constant for a first order reaction should be inverse seconds, s to the negative 1. Do the same analysis for a second order reaction where the rate law for a second order reaction is now concentration of A squared. So rate equals my rate constant times the concentration of A squared. Again, I'm going to divide both sides by A squared in this case. right? So that cancels out, and I have the rate constant equals rate divided by a squared now. So now I'm going to plug in the units that I have. So my rate constant equals rate, which is molarity per second. Now the concentration of A is squared, so concentration squared. And when I divide, molarity cancels out up here, and one of those molarities cancel out. So the unit of rate constant for a second order reaction is inverse molarity, inverse seconds. So the units for your rate constant will change, and they will depend on the order of the reaction. So here was our first order, and here is our second order reaction rate constant. You'd imagine, right, for a third order, we would have a rate constant would be molarity to the -2 inverse seconds. We'll most often see first and second order reactions and maybe occasionally see a third order reaction. But this is where the units come from. The units of the rate constant, they change because they're there to help us make sure that the rate of the reaction, when we do this calculation, rate always needs to be in molarity per second. But our concentrations, they may be concentration squared, or concentration cubed. So in order for that to clean up so that we're left with molarity per second, that's the function of the rate constant, as well as bringing a temperature component for the reaction. One other thing to consider in these reactions, in the early reactions we looked at, it was pretty easy to figure out, but let's look at this reaction of hydrogen reacting with oxygen to produce water. So for this reaction, for every 2 moles of hydrogen that react, we're going to need 1 mole of oxygen, and we're going to produce 2 moles of water. That's directly from the coefficients from the reaction. Now, in the reaction we looked at initially, there was just one starting material, and it was pretty easy to say, okay, I just track the disappearance of that starting material to find the rate of the reaction. There was only one product, so I can say, okay, I'm going to track the appearance of that product and determine the rate of the reaction. Now that we have a reaction with multiple starting materials, what do we look at to determine the rate of the reaction? Do we look at the disappearance of hydrogen? Do we look at the disappearance of oxygen? Or do we look at the appearance of water? And an example question to kind of think about when we're looking at a reaction like this, which component, the hydrogen or the oxygen, is being consumed at the fastest rate? And how does that rate compare to the rate that water is being produced in this reaction? Right, so if we think about it, what's being consumed at the fastest rate? So let's say we just go through this reaction as written, and we say that this reaction takes place in 1 second. So for this reaction to occur as written in 1 second, I would need 2 moles of hydrogen to react with 1 mole of oxygen. So that means, right, I would have 2 molar per second hydrogen reacting with 1 molar per second oxygen. We can use those coefficients to get a relative rate, right? We're using twice as much hydrogen as we are oxygen per cycle of that reaction. So hydrogen's reacting at twice the rate, right? For every 2 moles of hydrogen that disappears, I need to have 1 mole of oxygen disappear. How does that compare to the rate of water being produced? Well, for every 2 moles of hydrogen in, we get 2 moles of oxygen out. So going back to our 1 cycle of this reaction in a second, if 2 molar of the hydrogen disappeared in a second, right, was consumed in a second, that also means that 2 molar per second water would be created. So those would have equal rates. The disappearance of hydrogen would equal the appearance of water in this case. And if we were to compare that to oxygen, right, the appearance of water would occur at twice the rate, the disappearance of oxygen. We can get that information right from the coefficients from the balanced equation. Now let's look at that in terms of a calculation, using the coefficients from that balanced reaction to help us figure out the relative rates. So if I said that the rate of the disappearance of hydrogen, right, was 2 molar per second, what is the rate of disappearance of oxygen? Well, we would say that for every 2 molar per second of hydrogen that's disappearing, I know for every 2 molar of hydrogen, I need 1 molar of oxygen, just based on the coefficients from the reaction. So if hydrogen is disappearing at 2 molar per second, right, oxygen would be disappearing at half of that rate. It would be disappearing at a rate of 1 molar per second. Just using those coefficients from the balanced chemical equation to let us convert from the disappearance of hydrogen into the disappearance of oxygen, or the appearance of water in this case. So here's one more example where our coefficients are a little bit different. The breakdown of ozone, right? Ozone, 2 molecules of ozone, when they break down, lead to 3 molecules of oxygen. So let's say ozone is being consumed at a rate of 3.6 molar per second. What rate is oxygen being produced? And remember how we use the coefficients from the balanced chemical equation to help us relate those rates. So if ozone is being consumed at 3.6 molar per second of ozone, and I know from the balanced chemical equation for every 2 molar of ozone, I'm going to make 3 molar of oxygen. Calculate across, and my ozone cancels out. I multiply by 3/2. The rate of the appearance of oxygen would be 5.4 molar per second. Again, this is our conversion factor. We're just using the coefficients from the balanced chemical equation to help us relate for every 2 moles in of ozone, 3 moles of oxygen are going out. So if 3.6 moles of ozone are being consumed, right, well, I'd expect that 5.4 moles of oxygen are being produced at that same time. So we can use those coefficients to help us relate those different rates of the reaction. That is our conversion factor.